problems we discuss and the properties we discuss in this section are we will show that all Legendre polynomials satisfy the orthogonal property. That is, the sequence of Legendre polynomials are orthogonal functions. We can also see that any polynomial can be expressed as a linear combination of Legendre polynomial. However, we can say there are some conditions on functions that can be expressed as a linear combination of Legendre polynomials. So we will see a note on that. Finally, we will show that the best approximation of a function as a polynomial under least square method is exactly what is given in 2. That is, it should be a linear combination of Legendre polynomials. Now, coming to our first property, let us consider the sequence of Legendre polynomials P0 of x, P1 of x, etc. The most important property of the Legendre polynomials is that they are orthogonal functions. That is, if we take the integration from -1 to 1, Pm of x into Pn of x, then whenever m not equal to n, we get it as 0, and when m equal to n, it is a constant, that is 2 by 2n plus 1. Okay, so this is often expressed by saying that this is a sequence of orthogonal functions in the interval -1 less than or equal to x less than or equal to 1. So let us prove this. When m less than n, we will start with a function f of x which has at least n continuous derivatives on the interval -1 less than or equal to x less than or equal to 1. And we start with an integral I is equal to integral from -1 to 1 f of x into Pn of x dx. What we will see later that this I is actually this I is the same as integration from -1 to 1 minus 1 raised to n into nth derivative of x into this x square minus 1 all raised to n dx. Okay, so continuing, we know that by Rodrigues formula, the Rodrigues formula say that Pn of x is 1 by 2 raised to n factorial into nth derivative of x square minus 1 all raised to n. That is, if you replace this Pn of x with this expression, you can see that this is the same as 1 by 2 raised to n into n factorial into integration from -1 to 1 f of x into nth derivative of x square minus 1 the all raised to n dx. So let us do this integration by parts, that is taking f of x as the first function and this as the second function. We can see that this is same as 1 by 2 raised to n into n factorial into first function is, you can see that first function is f of x into integral of the second function minus, so it has limit from -1 to 1 minus 1 by 2 raised to n into n factorial integral of derivative of the first function, that is f dash of x into then integral of the second. Okay, then you can see that the first part of this integral is actually 0, since when we substitute 1 at this x square, you can see that this entire term becomes 0, and we have the same effect when -1 is substituted. So that is, we get this integral is equal to some -1 into 1 by 2 raised to n into n factorial integration -1 to 1 f dash of x into n minus 1 the derivative of x square minus 1 the whole raised to n. Okay, now if we proceed like this, we get just -1 all square integration from -1 to 1 and the second derivative of x into n minus 2 derivative of x square minus 1 all raised to n. Okay, so you will get like this when we take when we do the integration one more time. So if we do it for n times, you can see that this is -1 raised to n into 2 raised to n sorry, minus 1 raised to n by 2 raised to n to n factorial, integral from minus 1 to 1, the nth derivative of f into x square minus 1, the whole raised to n dx. Now remember that we started with m less than n and I is equal to this expression, and we reached at I is equal to minus 1 raised to n into this expression. However, we can see that if f of x is equal to pm of x, what happens? Then if f of x is equal to pm of x with m less than n, then you can see that the nth derivative, since m is less than n, the nth derivative of pm of x is equal to 0. Okay. Then you can see that fn of x must be equal to 0, and consequently we get the result that I is equal to 0 whenever m is less than n. So when f is replaced with the pm of x and m less than n, we can see that I is equal to 0. We now consider the case when m is equal to n. Now we once again start with the I is equal to integration from minus 1 to 1 f of x into pn of x dx, and we already showed that this is the same as minus 1 raised to n by 2 raised to n into n factorial, integration from minus 1 to 1 the nth derivative of x into x square minus 1 all raised to n dx. Now we are going to replace this f of x with the pn of x, which is the nth Legendre polynomial. Now by Rodrigues formula, we know that Pn of x is the same as 1 by 2 raised to n into n factorial and nth derivative of x square minus 1 the whole raised to n. So we can show that the nth derivative of this Pn of x is actually this expression. For what I can write is that the nth derivative, okay, of Pn of x is actually the nth d raised to n by dx raised to n of this expression. Okay, so it becomes once again the nth derivative of x square minus 1 the whole raised to n, and into 1 by 2 raised to n and factorial is there. Then this is same as the 2nth derivative of this x square minus 1 all raised to n is a polynomial with a degree x raised to 2n. So it starts with x raised to n minus a polynomial with a degree less than 2n minus 1. So when you take the 2nth derivative of this expression, you can see that you just need to calculate the derivative of the 2nth derivative of x raised to n, because all other terms have the derivative equal to 0. So this becomes 2n into 2n minus 1 into 2n minus 2 and so on. That is, this is equal to 2n factorial, and hence you can see that the nth derivative of the nth Legendre polynomial is 2n factorial into 1 by 2 raised to n into this n factorial. Okay, now let us substitute the nth derivative of Pn of x here. That is, I is equal to 2n factorial by 2 raised to 2n into n factorial whole square, integral from minus 1 to 1. Now you can see that there is a minus 1 raised to n. This minus 1 raised to n into x square minus 1 raised to n becomes 1 minus x square all raised to n into dx. Okay, and this is equal to 2 into 2n factorial, because you can see that this x square is an even function, therefore 1 minus x square all raised to n is also an even function. So you can replace this integration from minus 1 to 1 to integral from 0 to 1 by placing a 2 here. So this is 2 into 2n factorial by 2 raised to 2n into n factorial whole square into integral from 0 to 1 1 minus x square all raised to n dx. Now we continue this expression with by writing x is equal to sine theta. So when x is equal to sine theta, you can see that this becomes cos theta all raised to 2n, and dx gives you cos theta all raised to 2n plus 1. And also, since x ranges from 0 to 1, we can say that this theta ranges from 0 to pi by 2. So that the integration becomes I is equal to 2 by 2n factorial by 2 raised to 2n, then factor whole square, integration from 0 to pi by 2, cos theta the whole raised to 2n plus 1 d theta. Now let us compute this part. Now we can see that this is the same as 2 into 2n factorial divided by 2 raised to 2n into n factorial the whole square, and by the standard formula this is same as, so I can write this 2n plus 1, 2n, 2n minus 1, 2n minus 2, etc. Since this is an odd number, I can end up with a 3, 2 and 1. Okay. Now in order to calculate this, what I do is that I multiply the numerator and denominator with the same expression. Okay, that is, this is equal to once again I multiply the numerator and denominator with 2n into 2n minus 2 into etc 2 into 1 divided by again the same 2n into 2n minus 2 into etc 2 into 1. Now we can see that the numerator becomes, so already you have the numerator, it is 2 into 2n factorial into, now what is the numerator? Numerator, you can say that if you take a 2 outside from here and from here and here, then you will get just 2 raised to 2n n factorial all square divided by, and let us compare the denominator. The denominator, it is 2 raised to 2n into n factorial all square. Now you can see that the whole denominator becomes 2n plus 1 factorial. Okay, so it is 2n plus 1 factorial. So if you compute this value, you can see that everything cancels except a 2 in the denominator and 2n plus 1, 2 in the numerator and 2n plus 1 in the denominator. Thus we can see that this capital I is equal to integration from minus 1 to 1 f of x into pn of x dx, when when f of x is replaced with pn of x, this 2 by 2n plus 1, and when f of x is replaced with pm of x, when m less than n, gives you 0. So which is exactly what the orthogonal property, that is the we can finally conclude that all these Legendre polynomials are orthogonal functions. Now we will go to the next topic, Legendre series. Now we can see that using Rodrigues formula, we can write 1 is equal to p naught of x and x is equal to p1 of x, and for x square we can say that this p2 of x is equal to half into 3x square minus 1, so 2 p2 of x is equal to 3x square minus 1, and therefore you can write this x square is equal to 1 plus 2 p2 of x by 3, or you can replace this 1 with the p naught of x and write p naught of x plus 2 p2 of x by 3. Now we can see that similarly you can replace x cube as a linear combination of this Legendre polynomials. Okay, so for x cube we obtained that this is same as 3 by 5x plus 2 by 5 p3 of x, and where you can replace x with p1 of x, and this forms this takes the form 3 by 5 into p1 of x plus 2 by 5 into p3 of x. Now similarly applying this technique, you can see that any x raised to n can be replaced with a linear combination of these Legendre polynomials. If we consider a third degree polynomial, p of x is equal to p naught plus p1x plus b2x square plus b3x cube, we can see that we can replace each one of this 1x, x square and x cube with the Legendre polynomials, the corresponding expressions of linear combinations of Legendre polynomials, and finally obtain an expression which is a linear combination of the Legendre polynomials. Thus we conclude that any polynomial Pn of degree n can be expressed as a linear combination of Legendre polynomials up to degree n. Now let us see a problem. Now let us do a very simple problem. So we have to express x plus x square as a linear combination of Legendre polynomials. So we know that x is equal to p1 of x and x square is equal to 1 by 3 p0 of x plus 2 by 3 p1 of x. So just add them and we have the result. 1 by 3 p0 of x plus p1 of x plus 2 by 3 p2 of x. Okay. Now the next problem that we discuss in this section is, can you write an arbitrary polynomial f of x as a linear combination of Legendre polynomials? So if such an expression exists, then we can call it as a Legendre series. Now let us assume that such an expression as exists. Then you can write f of x into pm of x as summation over n equal to 0 to infinity an into pm of x. Okay, an into pn of x into pm of x. Then integrating from -1 to 1 both sides, you can obtain it as this is equal to integral from -1 to 1. Now f of x is there, or it becomes sigma an into pn of x into pm of x, which is equal to, so you can take that sigma over an outside. So integration from -1 to 1 pn of x into pm of x. Okay, there is a dx also. Now you can see that pn of x into pm of x is equal to 0 when m not equal to n, and 2 by m plus 1 when m equal to n. Okay, so 0 when m not equal to n and 2 by m plus 1 when m equal to n. Then this becomes, you can see that this value is not equal to 0 when only when n equal to m. That is, this is am into the product is 2 by m plus 1. So you can have a you can find a general formula for am using this technique. So we can, what we can write is that we can write am is equal to m plus 1 over 2 into integral from -1 to 1 f of x into pm of x dx. That is a general formula. An is equal to n plus half into integral from -1 to 1 f of x into pn of x dx. Now you can see that all these calculations are possible under the assumption that f of x has such a series, and this series is integrable term by term on the interval -1 less than or equal to x less than or equal to 1. Now we can see that when f of x is a polynomial, the condition is easily satisfied. But if f of x is a function of other type, any other type, then we cannot ensure the existence of such an an. So there comes the Legendre expansion theorem. The Legendre expansion theorem says that if both f of x and f dash of x have at most a finite number of jump discontinuities. Okay, so f of x can have at most a finite number of jump discontinuities, and f dash x can also have finite number of jump discontinuities. Then the theorem states that this an defined by the following formula exists for every point of continuity, and also at a point of discontinuity it converges to f of x minus f of x plus by 2. Where f of x minus is the left limit and f of x plus is the right limit, and this holds for every point between -1 and 1, which is the domain of the function f of x. Now here comes the last part of our discussion. So we consider the following problem. Let f of x be an arbitrary function. So can you approximate this function f of x by a polynomial p of x in such a way that the integral I from -1 to 1 f of x into p minus p of x the whole square dx is the minimum. So the problem is, what is the minimizing polynomial? The answer is, it should be the first n plus 1 terms of the Legendre series, summation an Pn of x, where an is given by the formula 2n plus 1 by 2 integration from minus 1 to 1 f of x Pn of x, which is given in the previous slide. Now, in order to prove that, let us start with the I, which is integral from minus 1 to 1 f of x minus p of x the whole square dx. So we need to find the minimum p of x such that this integral gives the minimum value. And we know that any polynomial of degree less than or equal to n can be expressed as sigma bn Pn of x. Okay, and we need to prove that this is precisely the same as sigma an Pn of x, where an is 2n plus 1 by 2 integral from minus 1 to 1 f of x into Pn of x dx. So we have to start with say I is equal to integral f of x minus p of x the whole square, and we need to find that p of x which minimizes this integral from minus 1 to 1. Now we know that any p of x can be written as sigma bk into pk of x. Okay, and we will finally show that this bk is precisely what ak is. Okay, now for that I start with this expression f of x minus sigma bk pk of x the whole square. So if I expand it using a minus b whole square, I will get an expression like this. So what is this? This is the square of the first term. So you can obtain this term. Now for the second term, we expected it to be summation bk pk of x into summation bk pk of x. I would like to write it like k equal to 0 to say n, and summation some m is equal to 0 to n bm pm of x. Okay, now let us fix some k in the first expression. Then if you multiply with it in with the second expression, you can see that a non-zero answer is obtained only when m is equal to k, and that answer will be 2 divided by 2k minus 1 into pk square. So this is how the square of the last term is. Now the second term is 2 times summation. Here you can see that bk can be taken outside, integral from minus 1 to 1 f of x into pk of x. But we know that by the formula ak is equal to say 2k plus 1 by 2 into integral from minus 1 to 1 f of x into pk of x. Okay, so that I can write the last term. So sorry, the new line becomes integral from minus 1 to an f of x square plus, okay, the first two terms are the same, minus 2 times summation bk into, this becomes 2 times ak by 2k plus 1, right? Now let me add say plus summation 2 by 2k plus 1 ak square minus summation 2 by 2k plus 1 ak square. So you can see that this whole term takes a new form, which I can write like summation this plus summation. This is exactly what bk minus ak the whole square is. Okay, taking 2 by 2k plus 1, summation 2 by 2k plus 1 common, then minus summation 2 by 2k plus 1 ak square. Now here comes the point that we need to minimize this integral. So we are assuming that p of x is a polynomial of degree n, and p of x is of the form summation bk pk of x. So for what value of bk that you can minimize this integral? So you can see that whenever bk minus ak is equal to 0, you can make this integral a minimum only when bk is equal to ak. So what I conclude is that So we already told that I assumes its minimum value when this bk minus ak is equal to bk is equal to ak for k is equal to 0 to n. So the only hypothesis we need at this stage is that both f of x and f of x square must be integrable. Now this also answer the following problem, that is, what is the best polynomial approximation of a function under the criterion of approximation using least squares. Now here are some problems to try yourself at home. So try to check what is meant by orthogonal polynomials, and you have an assignment. Try to submit the first three terms of the Legendre series of these two functions. We can see that these functions are either continuous and having gem discontinuities for the function and its derivatives. So by our one of the theorem mentioned before, you can see that the Legendre series exists, and you can submit its find and submit its first three terms. And so try to read more about the theorem mentioned on this topic, which I have mentioned as the Legendre expansion theorem, which answers what kinds of functions f of x have this Legendre series. So try to find out some time to watch this video, and thank you.